Hello, everyone. I hope you're all doing well. My name is Adil, and my team member is Ashar. And for our project, we worked on the lane detection task for autonomous vehicles using modified spatial CNN. This is the general outline of the presentation that we will follow. Lane detection is one of the most basic needs of an autonomous vehicle, without which safe navigation of the car is not possible. A vehicle which only needs to stay inside the lane markings, but also make sure it detects the kind of lane to safely turn. Fast and real lane detection is pertinent in the success of autonomous vehicles. There are a number of technical challenges. The task of lane detection is quite complex, and initially clustering algorithms were used for it. However, since the amount of data in a traffic scene is random and can contain any number of things, traditional techniques were not very effective. With advancements in deep learning, semantic segmentation provided much richer information to the vehicle using instance segmentation to make better decisions and carry out safe navigation in the traffic environment. Nevertheless, this approach is also very expensive to perform, and alternative approaches are greatly needed. So for our project, we chose one of those approaches for lane detection. Our model takes in an input of an image and produces an output with the predicted lanes. Some of the related work that is done in lane detection started with using RANSAG, that is a clustering algorithm, followed by very recently using semantic segmentation, and quite recently using RNNs and LSTMs. RNNs allow the power to using sequential information to predict the next outcome, which is very useful in a task like lane detection where real-time data has to be processed. Our dataset contained 4,000 images, and we used an 80-10 split for train validation and test. And also we generated labels from the JSON files. We pre-processed the data by normalizing it to center around zero mean. We also resized the images to reduce the training complexity, and we further rotated the images to introduce some spatial augmentation into the images. Our approach was to modify the spatial CNN architecture by improving the backbone that it used. The CNN model takes in raw input image and outputs probability map for each lane marking curve similar to semantic segmentation task. These probability maps are then passed through a smaller network to predict final cubic lines. So the original model was trained on VGG16, and we decided to change this backbone and reduce the complexity of the model. So we used multiple pre-trained models and sliced them to reduce the size of the models. As you can see here, using a sliced backbone greatly reduced the model size, where the original model was 157 MBs, but all the other models that we tried were 3 times smaller in size.
Hi, I'm Ashar, and I'll be going over the training process. So we used an update rule of SGD with necessary momentum, and we used 2 different loss metrics: cross entropy loss for identifying the location of the lane, and binary cross entropy loss for identifying the existence of lanes. You can see the training and validation loss curves. The training loss curve is fairly similar for all the models. Also, you can see the validation loss for all our selected models converge faster than the baseline. We also use 2 different accuracy metrics: the 2 simple accuracy metrics for identifying the pixel-wise accuracy, and the F1 score for capturing the false positive and false negatives. Here you can see the curves of the 2 simple accuracy. You can see that validation accuracy fairly tracks the training accuracy pretty well in all of our models. Also, here we compare the 2 simple accuracy and F1 scores, which also show that all the models have similar accuracy performance, with ResNext performing the best in both the 2 simple accuracy and F1 score measure. On the rightmost image, you can see the prediction of our model, and in the middle, you can see the ground truth, which is a pretty good prediction of the lanes. We also tested our prediction on various weather conditions. In part C, where there was a bright light, our module struggled, but it picks up in the next frame in D, where it correctly predicts the lanes. So in our conclusion, we can say that our modified backbone approach helped us to somewhat match and somewhat exceed the performance of the baseline model, and we are also able to reduce the model complexity by slicing pre-trained models. In the future works, we may test our model on more complex data sets, or try to identify lanes in challenging conditions like snow, or may also try this model for real-time lane detection. We would like to thank the core staff of CS231N and all teaching assistants for their relentless efforts in helping us to come up with these projects. And a big shout out to a class of 2020. Thank you so much.